That mobile phone in your hand is a stunning piece of technology that's almost completely useless without a network to power it. When you're at home or in the office, that's taken care of by Wi-Fi. But when you go out into the world, you need a cellular network to keep you connected. That's why you see cell towers all over the place these days.
We use cell phones every day to stay connected with our family, work, and communities. But have you ever thought about how your cell phone works? A carrier has an extensive network of cell sites and switches designed to send and receive signals from everyone's cell phones. To maximize coverage and network availability, carriers place cell sites throughout communities in strategic patterns, as each site can only cover a specific area and number of users. The strategic site patterns ensure that the coverage radius of adjoining sites, often depicted as hexagons, overlap just slightly to provide seamless handoff of calls between sites. As cells are to your body, cell sites are to your network. All must be properly connected to allow the coordinated transmission of information.
Hi, my name is Josh Kallenberg, and I'm here at the Van Nuys Airport in Los Angeles, California. I've been flying professionally for about 13 years, and now I have the pleasure of flying this Gulfstream G450, which is a lot of fun and exciting. And today, I'm going to talk to you about becoming a pilot. So, some of you might want to learn how to navigate an airplane. There's several methods that we use. Some of the basic methods that we use from the primary training is what we call pilotage. It's basically using references outside, buildings, towers, certain mountains as reference landmarks to navigate around. That's usually good for smaller airplanes or when we're in a fast-moving jet, when you're coming in the terminal environment or around the airport. You might use that method. Means of navigation is a radio navigation, and that's where we follow electronic signals to certain fixes on the ground or places on the ground. And we can use that in the en route segment. So as we're flying along, there's certain stations around, all around the country, around the world, where if you're within the range of it, we can track it and follow that beam to that fix.
Standing for Very High Omnidirectional Range, a VOR uses a ground station to provide azimuth information to the aircraft. The station is oriented to magnetic north and sends out 360 radials. Each radial represents a heading from the station. When visualizing a VOR, think of a bicycle wheel. Each radial is a heading from the station, so when you fly over the VOR and track a radial from the station, you are essentially tracking a heading away from the station. It is important to remember that VOR radials do not account for winds, so remember that your in-flight heading may be different from the radial which you are tracking. Eventually you will enter the cone of confusion once near a VOR. This will be apparent once the CDI needle begins to dance back and forth, followed by full deflection once over the VOR. If your aircraft is equipped with distance measuring equipment, or DME, it is known as VOR/DME, and provides distance information to or from a VOR.
DME is an aircraft system that measures the slant range distance from aircraft to ground-based station. The DME can transmit and receive one of 252 channels, spaced at 1 MHz intervals. The channels are split into X and Y channel. Each channel have 126 channels. Each channel transmit and receive on frequency that are spaced 63 MHz apart. This is air-to-ground signal, while this is ground-to-air signal. An aircraft sends an interrogating pulse, and the ground station transponder responds by retransmitting a strong answering signal to be received by the aircraft. The DME equipment on board the aircraft converts the signal from the DME beacon into a digital readout of distance in nautical mile.
Today I'll show you the bridge, the command center, the brain of the vessel. Entering through the stairs, we'll start off from the bridge wing. This barbecue stove looking thingy on both port and starboard bridge wing. It's a remote panel. Here you find controls for the bow thrusters, indicators for speed, engine RPM, rate of turn, heading, compass, speaker and mic. This is a gyro repeater for taking bearings of objects or celestial bodies. This tall chair is a pilot chair. There is always a designated pilot chair for maritime pilots, no matter what type of ship you're on. An azimuth ring, used in conjunction with the gyro repeater outside for taking bearings of objects. SART on each side of the bridge. SART is short for Search and Rescue Radar Transponder. This is what it looks like when it's activated. The other ships can locate you from the radars. Fire plan, damage control plan, dangerous good plan, all for emergency use.
Most unfortunate, Captain. There's no stopping it. Titanic will founder.
Moving on to the center console, this is where most of electronic navigation equipments are. Starting from the port side, we've got 3 radars. 1 radar antenna on the forward mast and 2 at the back on the main mast. Numerous indicators. LORAN-C, which no one uses anymore. AIS, Automatic Identification System for ship. ACDIS, short for Electronic Chart Display Information System. It's a digital version of paper charts.
Gents, I give you the fountain of youth.
Sadly, we still use paper charts in conjunction with electronic charts. It's a digital version of paper charts.
Gents, I give you the fountain of youth.
Sadly, we still use paper charts in conjunction with electronic charts. We still use paper charts in conjunction with electronic charts.
That just makes no fucking sense. I mean, it's just bullshit.